I'm Sachini Pioni Ekanayaka. I'm a PhD student at the Department of Electrical and Computer Engineering, University at Albany, State University of New York. I'm working with Dr. Daphne Sais from the same department. Our paper is on sequential Bayesian network structure learning. So now let's get started. In many real-world applications, example medical diagnosis, behavioral analysis, Bayesian networks are used to describe relationship between variables. For an example, in medical diagnosis, the cancer Bayesian network is shown here. It consists of 5 nodes that represent the factors that might affect a patient's chance of having cancer. In this context, a very important task is to learn the underlying structure of such networks. Thus, an increased interest in Bayesian network structure learning, where the goal is to identify structure of Bayesian network that best describes relationship between variables, has emerged. In this context, domain knowledge and our existing data can be used to learn the structure of the Bayesian network. Now I am going to briefly describe related work. Various heuristic methods have been proposed and typically used due to the complexity of the structure learning problem. For instance, hill climbing constitutes a greedy algorithm that learns a structure by maximizing a given score. At the same time, various methods have been proposed to speed up the process of structure learning from data within a restricted search space. For example, the Charlo algorithm learns a tree-structured Bayesian network where the result is suboptimal. On the other hand, in many real-world applications, example monitoring patients in the medical domain, expert knowledge is typically available, but expert elicitation is expensive and time-consuming. In this paper, we propose an approach to speed up structure learning without compromising accuracy by evaluating most prominent relationships early on. Specifically, we consider the set of candidate network structures as our hypothesis space and devise a method that sequentially evaluates possible variable relationships. The goal is to accurately learn the underlying Bayesian network structure from existing data in less time. Now I am going to describe our problem with specific parameters. We consider a set of x n discrete random variables with a joint probability distribution P star. We assume there is a gold standard Bayesian network G star induced by the joint distribution P star. G star is a directed acyclic graph having discrete random variables V as nodes, and epsilon is the set of directed edges. We consider a finite number M of hypotheses, each of which corresponding to a single DAC, and we denote it as G1 to Gm. This constitutes the hypothesis space. We denote E as the set of distinct relationships between any two random variables in X. Here the directionality is not considered. Ek represents the value of time and effort spent in evaluating variable relationships. Cij denotes the cost of selecting hypothesis Gj when the true hypothesis is Gi. Here, a Bayesian network considered as a collection of information, and it is quantified using mutual information. So, IDEK is the information content in EK given the dataset D. IDGI considered as collection of information distributed among the edges. Objective is to accurately identify Bayesian network structure in hypothesis space from existing data in less time by evaluating most prominent relationships early on. This is our optimization setup. Consider a pair R-dr of random variables associated with the sequential evaluation process of EK. Random variable R represents the last variable relationship selected from the set E. Random variable dr denotes the decision of selecting DAG among impossible choices. Our goal is to minimize this optimization function with respect to R and dr. First term denotes the total cost of evaluating R variable relationships in the sequential process, while the second term penalizes the DAG decisions. To solve the optimization problem, first consider the posterior probability phi k vector as shown here. Based on this posterior probability and dynamic programming, we derive the optimum stopping strategy. The last stage is defined as L function. This represents the optimum cost to go at the last stage, which is equal to cost of stopping G phi k. In any intermediate stage, the optimum cost to go is defined as minimization of two functions, cost of stopping and cost of continuing. Here we find the cost of stopping G phi k using misclassification cost defined as a C matrix and posterior probability phi k. Cost of continuing L tilde function is defined here. Finally, the optimum classification strategy dr star is given by this equation. The proposed approach consists of pre-processing and a graph learning phase. During the pre-processing phase, the optimum decision and stopping strategies described are solved offline. Specifically, all possible posterior probability vectors are computed by quantizing the Belief space for each variable relationship Ek. We use mutual information to estimate the importance of variable relationships in E and appropriately rank them. During the graph learning phase, the numerical solutions found during preprocessing are employed to select and assess the suitability of variable relationships. Specifically, our proposed approach begins by initializing the posterior probability. Then we evaluate each variable relationship Ek and update posterior probability phi k. If cost of selecting and assessing the suitability of a particular relationship is greater than the cost of making a decision, we stop Ek evaluation and make the optimum decision. This process is repeated until a decision is reached by selecting a subset of available relationships or the suitability of all variable relationships in E is assessed. To test the performance of our proposed approach, we use two standard Bayesian networks, student network and the sprinkler network, and use the associated probability distributions to randomly generate 1000 samples each. Next, the hypothesis space. Here, NGI denotes the number of edges in graph GI. So we consider a reduced hypothesis space consisting of graphs that belongs to these four categories. For instance, this describes a graph GI with number of edges less than number of edges in G star, the gold standard network. Likewise, this represents the number of edges in graph GI greater than the number of edges in G star, and so on. In our experiments, we set m equal to 6, assume misclassification cost Cij equal to 1, where I is not equal to j, and Cii equal to 0. Ek is the variable relationship evaluation cost. We assume the same evaluation cost E for each variable relationship Ek. 5-fold cross-validation results are reported here onwards. We assess performance with respect to these matrices. For instance, correct edges, CE, is the number of edges present in both optimum decision graph G tilde and G star with correct orientation. Likewise, this set of matrices are to compare the optimum decision graph G tilde with gold standard network G star. Further, we selected hill climbing and Charlo algorithm as baselines to compare the proposed approach. Now let's look at the results. This graph illustrates the variation of correct edge matrix as a function of number of dataset generated from the sprinkler network. We observe that the proposed approach succeeds in identifying on average high number of edges compared to the two algorithms. Furthermore, the value of the CE matrix stabilizes around 500 datasets. Therefore, for the rest of the experiments, we generate 500 datasets and reported average results. This figure illustrates the variation of correct edges and graph error as a function of variable relationship evaluation cost E for the sprinkler network. As expected, different variable relationship evaluation cost leads to different CE and GE value, while evaluating less variable relationships leads to lower CE and thus higher GE value. We underscore that the learning time metric is also reduced when the variable relationship evaluation cost increases, since less relationships are evaluated in this case. Thus, an optimum decision is reached in a shorter learning time. This table reports average statistics for bar evaluation matrix on the sprinkler network and student network for the proposed approach, hill climbing, and Chaulo algorithm. From these results, we see that the proposed approach, irrespective of its simplicity, achieves competitive performance against well-known structured learning algorithms considered here. Specifically, for both networks, the number of correct edges is higher than that identified by hill climbing and Chaulo algorithm. Even though our hypothesis space consists of both denser and sparser graph, our proposed approach is able to balance between maximizing information content and sparsity to favor the graphs that are most related to G star. Also, we underscore that our approach is able to prioritize edges with high information content. In contrary, hill climbing start with a random network, manipulating one edge at a time until the local maximum of a given score is found. However, in our approach, we do not necessarily evaluate all variable relationship, thus saving a considerable amount of time. In summary, we introduced a method to speed up graph learning time without compromising accuracy given finite set of candidate graphs. The performance of proposed method validated on existing Bayesian networks with respect to existing heavily used structural learning methods. Finally, as future work, we plan to explore methods to decrease preprocessing time, to extend proposed approach for larger Bayesian networks, also to address problem of hypothesis space selection by exploring hierarchical hypothesis classification approach. Thank you so much for listening to my presentation. If you have any questions, feel free to email me. Thank you.